In the previous chapters, we looked at the general basics of equilibrium. We then focused on acid-base equilibrium, and here we're going to look at some more advanced aspects of equilibrium. Specifically, what we're going to look at is buffers, which involves acids and bases, and titrations, which also involve acid and bases. And then finally, we're going to look at the product solubility constant, which is essentially the equilibrium of a relatively insoluble solid dissolving in water. So that's the focus of this chapter. The first thing that we're going to talk about here is buffer solutions, which can resist a change in pH when an acid and a base is added. A very important buffer solution to you is blood. So blood is able to reduce or minimize changes in pH when acids or bases are added, which is very important to our physiological function because different enzymes and such only work at certain pHs. So it's a very important concept. We're not going to talk about blood too much here or the biology of this. We're just going to talk about the basics of buffers, which, as you'll see, may not seem as basic once we get into all the details. Before we do that, though, I want to talk just for a second about indicators. And the point of this chart is to show you that there are different indicators that work for different things. So, for example, methyl orange, which you can see here, works around 3 to 4, 3 to 5 pH range, turning from a reddish color to an orange or a yellowish color within this range. One that you may have used before, phenolphthalein, which turns pink somewhere around a little over 8, approaching 9, although here it looks like it's almost 9. I thought it was slightly lower than that. But this is basically just some indicators. Why do we care about indicators? Well, indicators can be used to monitor the progress of acid-base reactions. And as I mentioned a minute ago, we're in 2 of the 3 sections of this chapter, we're going to talk about acid-base reactions. So these are a way in order to monitor those reactions. As an example, buffers. All right, so here we have an unbuffered yellow solution, and here we had a pH 8 buffered yellow solution. We've added methyl orange indicator to that. If you recall, methyl orange indicator is going to change colors at low pHs. So it is yellow at these higher pHs, and it is red at lower pHs. We add 1 milliliter of 0.01 molar HCl solution. What you'll notice is that the buffered solution, the methyl orange, stays yellow because the buffer minimized the change in pH. There was a relatively small change in pH. But the unbuffered solution didn't. So the unbuffered solution didn't resist a change in pH, and it went from the yellow color to this red color as shown here. So this basically shows us that the buffer is able to resist a change in pH visually, and the unbuffered solution is not. What's important to note here is that a buffer solution can resist a change in pH whether acid is added or base is added. It's also important to note that if we got out the bottle of 12 molar HCl, and for safety reasons you might not want to do this, but if we got out the bottle of 12 molar HCl and we started pouring it into this buffer solution, we could certainly get this buffer solution to turn red. Buffers don't resist changes in pHs if large amounts of acids and bases are added. So that's something else we're going to talk about here. But what's interesting for now is, how is it possible that we could have a solution that resists changes in pH whether an acid is added or a base is added? They must have species in there that can react with both acids and bases. So what we want to talk about next is, well, how exactly do they do that? Well, buffers take advantage of using a weak acid and its conjugate base. So a solution is made that contains both weak acid and the conjugate base. Not simply the conjugate base that's made from the interaction of the weak acid with water, but literally this is called sodium acetate. Sodium acetate is added to the solution. So there is a concentration of weak acid and a concentration of weak base. Another way that a buffer could be made is to use a weak base, ammonia, and its conjugate acid, ammonium, NH4+. Very much like you can't have a bottle of CH3COO-, which we talked about in the previous chapter, you can't have a bottle of NH4+. You need a counter ion. chloride is a common counterion. So in this case, we have NH4Cl because the NH4 is plus, the Cl is minus, and the charges balance out. So, take-home message. Buffers can be made from a solution of weak acid and the conjugate base, or a solution of weak base and the conjugate acid. In the case where we have, well, I should switch to the next slide and talk about that. In the case where we have a weak acid and its conjugate base in solution, we have this equilibrium reaction occurring, where the acid, okay, is reacting with water to form H3O plus and CH3COO minus. Remember, the buffer is not made by simply adding this, the acid, and letting it react with water and getting a relatively small amount of this. We talked about Ka in the last section, and you'll recall that this was often less than 5% of this. So basically, this is not how we're going to make a buffer. How we're going to make a buffer instead is we're going to actively add this and actively add this in the form of its sodium salt, for example, or potassium salt. Okay, so we would add acetic acid and sodium acetate. Well, what happens if we then add an acid? Well, if we add an acid, it's going to react with the conjugate base. And when it does, it forms a little bit more acid of the acetic acid. And what happens is we now have a higher concentration of acid, assuming we started with a 1-to-1 mixture, and a lower concentration of the conjugate base. But because this acid is a weak acid, the change in pH is relatively small. If we just added H3O plus to straight water, it would increase the concentration of H3O plus by the exact amount that we added. But if we add this H3O plus to a solution with this weak base, we form this. And because this is an equilibrium where a very large percentage of it stays as this compound and not as this compound, then the change in pH is relatively minor. Well, what happens if we add a base? If we add a base, the exact opposite happens. The OH minus reacts with the acid. In this case, this is the acidic proton. So the OH minus takes away this acidic proton, forms water, and more of the conjugate base. So the conjugate base concentration increases and the acid concentration is decreased because some of it reacted to form the conjugate base. Again, the conjugate base has a relatively minor change in the pH as compared to the strong base. So you're essentially turning the strong base into a weak base by adding a weak acid. And you are turning the strong acid into a weak acid by adding the conjugate base. So buffer solutions are able to resist changes in pH, whether acid or base is added, which is quite remarkable when you think about it. But this is how it's actually accomplished. Now, a few notes about practicality. Okay, and we talked about this a little bit in the last chapter for the acids, but we didn't talk about it for the bases, so I wanted to bring it up one more time. If we have the acid, HCN, acting as an acid, it's going to lose an H+. So the conjugate base of this is Cn-. You can't buy a bottle of Cn-. You can't put Cn- in a bottle. You can't put a bunch of negative ions next to each other. But what you can do is have a counterion, such as Na. Okay, and this stabilizes the charge. So you have Na plus, Cn-, you have a neutral salt, and you can get NaCN. Now, can you actually buy NaCN? Maybe not, because it's sodium cyanide. All right, so this is a toxic compound, okay, but it still illustrates the point. All right, here we have sulfurous acid. In this case, the conjugate base is HSO3-. Again, the sodium salt of this is NaHSO3. So if we added a mixture of H2SO3 and NaHSO3, we would have a buffer. We're not going to make a solution of H2SO3 and HSO3- because we're not going to be able to get HSO3-. We're going to have a counterion. This counterion simply acts as a spectator ion. And we talked about this quite a lot in the last chapter. Here, I want to mention how this works for bases. It's the same idea, except now the counterion needs to be negative, right? Because the thing you're going to get is plus, so you need a negative counterion. So sodium isn't a good counterion because it's already plus, and you're not going to have two positive ions in the compound. So here we have NH3 acting as a base. What is the conjugate acid of this? Well, if this acts as a base, it gains an H+. So now we go from 3 H's to 4 H's and also a positive charge. Well, NH4+, for the same reason you can't have a bunch of negative ions next to each other, you can't have a bunch of positive ions next to each other, it needs a counterion. The counterion needs to be negative, in this case, Cl. So NH4Cl and NH3 will make a buffer. You're not going to make a buffer directly with NH3 and NH4+. Now, actively in solution, these are what are going to be the buffer. But to actually make it practically, you need to use this compound. Same thing here for methylamine, CH3NH2. The conjugate acid, it gains an H and a plus charge, and we use a chloride to counterbalance that. Now, could you use a bromide or a nitrate or something like that? Certainly you could. These are just examples of chloride salts, just like these are examples of sodium salts, which you could also make potassium, and even other things. Although there are solubility issues sometimes, and 1A metals tend to be inexpensive. Chlorides tend to be inexpensive. So these are, popular choices, but they're certainly not the only choices. Next thing we want to talk about is something called the Henderson-Hasselbalch equation. And I debated whether to show the derivation of this equation and ended up deciding not to. This is exactly the same as the Ka equation, but two things. One, it's rearranged, and two, we took the log of everything. So we took the log of H plus and we made the pH. We took the log of the Ka and we make the pKa, the negative log. And we took the negative log of the concentration of acid over base. We rearrange and we get pH equals pKa plus log concentration of base over concentration of acid. This is incredibly useful. So if we make a solution containing H2SO3 and NaHSO3, if we know the concentration of H2SO3 and we know the concentration of NaHSO3 and we know the pKa of the acid, we can find the pH of the solution. Very useful. I should note, because if you take a class like quantitative analysis, this may come up, that this assumes that the concentration of the weak acid/base are small compared to water when you add them to pure water. Said another way, it assumes the exact same thing as we made the assumption when we ignored x, so we didn't have to use the quadratic equation. So if you can't make that assumption, you can't use this equation. That said, just like in the previous chapter where we never used the quadratic equation, in all examples presented here, you can assume that this equation works. So let's do a couple of examples here where we look at the basically, applying this knowledge that we just gained. As usual, I'm going to switch over here to the camera in order to be able to write on this. So it says identify the solutions that would make an effective buffer. Remember that in order to make an effective buffer, we need to have a weak acid and its conjugate base. So there's a couple things that'll make an ineffective buffer. One is you have a weak acid and you have something that's not even related to it, all right? So let's say you have a weak acid, HF, and you add Cl minus, all right? This is not the conjugate base. Oh, you can't see that. This is not the conjugate base of this. So this combination just doesn't make sense, okay? So that wouldn't be an answer. You're not going to see too many like that. The other thing that won't work is a strong acid and its conjugate base. Strong acids and bases do not make buffers, okay? You can't, that's just not going to work. So essentially, you need a weak acid and its conjugate base. The other option, of course, is a weak base and its conjugate acid. So let's take a look at here and see what we've got. So this is another way of writing acetic acid, C2H3O2, with the H out front. In this case, we have a weak acid. How do I know it's a weak acid? It's not one of those 6 strong acids, same as last chapter. And is its conjugate base NaC2H2O3? All right. In this case, there's a typo here. This should be C2H3O2, and this is a conjugate acid-base pair. Okay, weak acid, conjugate base. HNO3, KNO3. In this case, HNO3 is nitric acid. That's a strong acid. KNO3 is its conjugate base because it's a source of NO3 minus. However, you got strong acid. It's not going to work. All right. NH3, a weak base, not one of the strong bases. And NH4Cl is its conjugate acid. That one will work. KOH, a strong base, and H2O is its conjugate acid. Unfortunately, since this is a strong base, that's not going to work. HCl and NaCl. Cl minus is the conjugate base of HCl. However, HCl is one of those strong acids, so that's not going to work. HF, NaF, yes, this one's going to work. You have HF and F minus, weak acid, conjugate base, that's going to work. HNO2, nitrous acid, and KNO2. All right, so this ion, NO2 minus, is the conjugate base of HNO2, so that one's going to work. All right, CH3NH2 and CH3NH3Br. In the previous slide, we showed Cl, but in this case, we used a bromide salt instead. And that one is absolutely a weak base and its conjugate acid. So, take-home message, you need a weak acid and its conjugate base, or a weak base and its conjugate acid in order to make an effective buffer solution. Now, let's actually do something where we have to calculate a pH. It says, what is the pH of a solution that contains 0.25 molar formic acid and 1.175 molar sodium formate? And then it gives us the pKa of formic acid is 3.74. So if you'll recall on the previous slide, we talked about the Henderson-Hasselbalch equation, which is an easier way of solving this problem than trying to use the Ka expression directly. So that is the pH equals the pKa plus log concentration of base over concentration of acid. And I'm not going to do this every time, but for this specific example, since it's the first time we're using this, I want to rewrite this equation with the actual base and acid that we have in this problem. So the pH equals the pKa plus log. Which one of these things is the base? Well, formic acid is the one with the H. Sodium formate is the one, this is CHO2 minus, okay? So this one is the conjugate base. So in this case, it's going to be the concentration of NaCHO2 on the top, and on the bottom, concentration of HCHO2. All right, so pH equals pKa, we're given 3.74 plus log of the 0.175 molar over 0.250 molar. And when we do all that math, we find that the pH equals 3.59. All right. Now, one thing that I always do to kind of as a sanity check, if you will, in order to check the math, is think about, should the pH be higher or lower than the pKa? Well, let's think about this in two ways. One mathematically and one practically. All right. So the basic idea here is that the log is negative if this number is less than 1. Well, when is this number less than 1? Well, it's less than 1 when you have more acid and less base, right? If the acid concentration is higher and the base concentration is lower, this will be a fraction of 1, and the log will be negative, so the pH will be less than the pKa. And exactly the opposite is true. If this number is greater than 1, then the log of it's going to be greater than 1, and it's going to be positive, I guess I should say. It's not going to necessarily be greater than 1, but it is going to be a positive number. So if the base concentration is higher and the acid concentration is lower, this number will be greater than 1, and this log will be positive, and the pH will be higher than the pKa. So mathematically, when we have more acid, okay, the pH is lower than the pKa, and when we have more base, the pH is higher than the pKa. Now let's think about it practically. Having extra acid, okay, like we do in this case, should that make the pH higher or lower? Well, extra acid should make the pH lower. So if we look at the pKa as 3.74, we have more acid than we have base, I would expect the pH to be lower than 3.74, and it certainly is. If we had more base than acid, then we would expect the exact opposite, and the pH would be higher than the pKa, but we don't have that in this case. So it's just kind of a sanity check just to make sure that we did the math properly and that our numbers make sense. Okay. All right, let's look at another example. Sorry, stuck. All right, so let's look at another example. It says, what is the pH of a solution that contains 0.185 molar NH3 and 0.125 molar NH4Cl? And then it tells us the pKb of ammonia is 4.75. Now this is an extremely similar question, but it's not exactly the same. In this case, we have pKb instead of pKa. You'll remember that pH equals the pKa plus log concentration base over concentration acid. In this case, the base is the NH3. So the pH equals the pKa plus log of the concentration of NH3 divided by the concentration of NH4Cl. So in this case, the base is this one, and the acid is this one, because this is the conjugate acid of this weak base. The problem here, of course, is we don't have the pKa, we have the pKb. Well, we talked about in the previous chapter that Ka times Kb equals 1 times 10 to the minus 14. This also means that the pKa plus the pKb equals 14. I just take the negative log of all of these things, and that's how I get this. All right, so now I can find the pKa. The pKa equals 14 minus the pKb. In this case, the pKa equals 14 minus 4.75. So the pKa equals 9.25. Now that I have this, I can plug in here. So it's going to be 9.25 plus log. The concentration of NH3 is given 0.185 molar. And the concentration of NH4Cl is given 0.125 molar. When I do all that math, I find that the pH equals 9.42. If I notice, the pH is higher than the pKa. That means I should have more base. Well, if I look here, NH3, my base, is higher in concentration than NH4Cl, my conjugate acid, which is lower in concentration. So what I would expect the pH is higher than the pKa, which it is. So the next thing that we want to talk about is looking at what happens to buffer solutions when we add acid and base. And we talked about before what happens from a theoretical perspective, but in this case, we're going to actually apply some numbers to that theoretical perspective. So here, what happens if we add a strong acid to this buffer? Well, if we have a buffer containing HF and NaF, and we add a strong acid like HCl, what's going to happen to the concentrations? Well, the concentration of F- is going to decrease, and the concentration of HF is going to increase. There is, of course, a buffering capacity, like we talked about before. If I have a lot of HCl, I might completely ruin the buffer, and we'll talk about that at the end of this section. What happens if NaOH is added? Well, if the NaOH is added, the HF reacts with the NaOH, we get more F-, and we have less HF. So certainly, adding HCl and NaOH are going to change the pH of a buffer solution. That being said, they should change the pH of the buffer solution much less than if it were pure water. assuming, again, that we don't go over the buffering capacity. Said another way, if we have 0.1 moles of solution of this in solution and we add 10 moles of this to the solution, then certainly you are not going to only have a small change in pH, because we've added, 100 times more of this than we have. All right, and it doesn't have to be to that extreme. So let's look at an example here, which again I'm going to go through on the camera, and we're actually going to do two like this because these problems are quite involved, and I think seeing it a second time can be helpful. It says a buffer solution with a volume of 525 milliliters is made with 0.125 moles of acetic acid and 0.1 moles of sodium acetate, the conjugate base. If 1.5 grams of NaOH is added without changing the volume of the solution, what is the pH of the resulting solution? So this question is annoying because they give us moles and volume. They don't give us molarity. So it turns out we actually have to calculate the concentration of everything in solution before we can think about what's going on in the reaction and solve the Henderson-Hasselbalch equation. So in order to do that, the first thing that I need is the concentration of HC2H3O2. Note that it does not matter at all which order that you do these in, but I'm going to do this in this one first, all right, just because it came first. All right, remember we need molarity or concentration, moles per liter. So I'm going to take the 0.125 moles, and I'm going to divide by, this in liters, divided by 1,000, 0.5250 liters. And when I do that math, I find that this is 0.238 molar. I'm going to repeat that same thing for the NaC2H3O2, or the conjugate base of the acetic acid. So NaC2H3O2. I'm going to, again, using the moles of this one, the 0.100 moles, divided by the 0.5250 liters, and the concentration of this one before we add the base is 0.190 molar. Now I have to find the concentration of NaOH that I have added. The problem is for NaOH, I'm given it in grams. So I need to convert from grams of NaOH to moles of NaOH. And then I want to divide by the liters, and moles divided by liters will give me the molarity of the NaOH. So starting with 1.50 grams of NaOH times 1 mole of NaOH. Look up the molar mass on a periodic table or Google it. So it's 40.00 grams of NaOH times 1 over, because I have to divide by liters, so multiply by 1 over the volume in liters, which is 0.5250 liters. And I find that the concentration of NaOH is equal to 0.0714 molar. So before I could do anything, I had to find the concentrations of all these things, which is, kind of an annoyance, but it's something we have to do. So before we add this, okay, we need to figure out what looks like an equilibrium table. And it's not exactly the same because it's more like a reaction table, but it's the same idea. So I've put my concentration of OH minus, my concentration of acetic acid, and my concentration of sodium acetate here, because these are the things that I'm going to need to plug into the Henderson-Hasselbalch equation. Specifically, I'm going to need this one and this one. Note that I need to be aware that the OH minus in the sodium hydroxide is going to react with the acid. So I'm going to have less acid when I'm done and more acetate when I'm done. I'm going to have less of the weak acid and more of the conjugate base, as we discussed in the previous section. The acid reacts with the strong base. In the opposite case, the base reacts with the strong acid in future examples. So in this case, before the base is added, how much OH minus is in solution? We're going to assume that it's 0. Okay. How much acetic acid is in solution? Well, we know that. It's 0.238 molar. All right. And how much sodium acetate is in solution, or how much acetate is in solution, is 0.190 molar, because we got the concentrations a minute ago. We add base. How much base are we adding? We're adding 714 molar base. Well, what's that going to do to the concentration of acid and the concentration of acetate? The acid is going to get used up. And since they're 1-to-1, I'm going to lose 0.01, I got to not mess that up, 714 molar of the acid. And I'm going to get extra of the acetate, the conjugate base. So I'm going to add 0.0714 molar acetate after. So here, the final concentration of OH minus is 0. Okay, so I guess what I should have done to make this look a little bit better is to put this as 0.0714. We're going to lose all 0.0714, and then we're going to have none left. Okay. In this case, we have 0.238 minus 0.0714, which is 0.167. So I just subtracted those two numbers. And in this case, I'm going to have 0.190, and I'm going to add the 0.0714, and I'm going to get 0.261 as the new concentration of this one. Now, I have the concentration of acetic acid. I have the concentration of acetate, and I can now solve the Henderson-Hasselbalch equation. All right. So the pH equals the pKa plus log concentration base over concentration of acid. Now, in the solutions manual, it tells you that the pKa equals 4.74, which I deleted when I deleted this to make this video. So now the pH equals the pKa, which is 4.74, plus log, the base is this one, 0.261, divided by the acid is this one, 0.167. And when we do all that math, we find that the pH is 4.93. It again makes sense that the concentration of base is, since the concentration of base is higher than the concentration of acid, we have a slightly higher pH versus the pKa, as discussed in the previous two questions. Because this example is a little bit complex and a lot of steps, I do want to go over another one. In this case, we're adding acid instead of adding base. So a buffer solution with a volume of 86.2 milliliters is made with 0.0585, it should say moles, of HF and 0.0866 moles of NaF. If 5.5 grams of HCl is added without changing the volume of the solution, what is the pH of the resulting solution? So again, we need to first find the molarity of each of the different things. So for HF, all right, we have the moles and we have the volume. So we want to take the 0.0585 moles and we want to divide that by the volume in liters. So divide that by 1,000, which is 0.0862 liters. And when I do that, I get 0.679 molar. I now want to repeat that for NaF. So for the concentration of NaF, I want to take the 0.0866 moles and divide by the 0.0862 liters, and I get 1.00 molar. For the HCl, I again want to go to grams to moles and divide by liters. So I want to take the 0.550 grams of HCl times 1 mole of HCl, and you can look up the molar mass on the internet or just from a periodic table, divided by 36.46 grams of HCl, times 1 over the volume in liters, so 0.0862 liters. And I find when I do all that math that we have, what is it here, 0.175 molar HCl. So just like in the previous question, I solve for the molarities of the different species in solution. I should also note that once I have these, I can set up this same table that looks like an ice table, but it's not exactly the same thing. So here I have H plus from HCl, and it's going to react with F minus to form HF. Again, we have to decide, is the acid going to react with the HF to make more HF, or is it going to react with, to make less HF, or is it going to react with the NAF to make less NAF or to make less F minus? Well, we have H plus reacting with the conjugate base. The acid reacts with the conjugate base to make more of the weak acid. So the initial concentration of this, okay, is 0.175 molar. The initial concentration of the F minus is 1.00 molar. And the initial concentration of the HF is 0.679 molar. Since there's less H plus than F minus, I'm going to use all of this. So I'm going to lose all 0.175 molar, and I'm going to have none left after, this should say acid. I copied it from the other one. This should say acid in all cases. So after the acid is added, I have none left. What about F minus? Well, the acid is going to react with the F minus to form less F minus. So I'm going to lose 0.175 molar of that. And I'm going to gain 0.175 molar. I'm going to get rid of the symbols here, or the units, all right, of that. Now I can do my math. And here I get 0.825. That should be a 2. 0.825 molar for the concentration of F minus, and for the concentration of HF I get 0.854 molar, which I could have written in the box, but I didn't. So the pKa of HF is equal to 3.17. We can use the Henderson-Hasselbalch now because now I have the concentrations. pH equals pKa plus log concentration of base divided by concentration of acid. When I do that math, I get that the pKa, which is 3.17, plus the log of the concentration of base, which is the F minus, 0.825, divided by the concentration of acid, which is the HF, 0.854. And when I do all that math, I find that pH equals 3.15. Again, a sanity check. The pH is slightly less than the pKa. The concentration of acid at the end of the solution is slightly higher than the concentration of the base, so that is to be expected. So, quite a lot of work in these problems. In the next examples, we'll look at a couple things that are slightly more straightforward. So as we mentioned before, pHs of buffers are more stable than the pH of a water solution. So if we add a little bit of acid or a little bit of base to a buffer, it will resist the change in pH. What we want to look at in this section is essentially two different types of examples. The first is the buffer range. What pHs can you make with a specific weak acid and conjugate base combination, or weak base and conjugate acid combination? The other thing we want to look at is the buffering capacity. So generally speaking, okay? The buffer will be effective when the concentration of base to concentration of acid, this ratio, is between 0.1 and 10. Said another way, it could be you have 10 times more base and it's equal to 10, or you have 10 times more acid and it's equal to 0.1. Once you go beyond 10 times more acid or 10 times more base, it becomes less effective. Well, let's think about this mathematically. If we have 10 times more acid and this value then becomes 0.1, the log of 0.1 is -1. So the pH equals the pKa minus 1. If the concentration of base is 10 times higher and this ratio is 10, the log of 10 is 1 and the pH equals the pKa plus 1. So this leaves us with a fairly simple mathematical formula, which is the pH for a buffer can be about 1 pH unit above or below the actual pKa of the weak acid or weak base. So in this case, it's going to be the pKa plus or minus 1. Let's look at a very straightforward kind of simple question. It says, what is the effective pH range of buffers formed with the following acids? The take-home message of this is the effective pH range depends on the pKa of the acid or base. So that's what's going to determine the effective range. So if the pKa of hydrofluoric acid is 3.17, we could make the pH down to 2.17 when we have 10 times more acid, up to 4.17 when we have 10 times more base. So essentially, we go from -1 when we have more acid, so 3.17 comes 2.17, to +1, which is 4.17 when we have 10 times more base. What about for acetic acid? Well, it's the same thing, right? It's going to be 3.74 to 5.74, plus or minus 1. And then finally, ammonia, that should be a pKa of 9.25. So in this case, it's going to be from 8.25 to 10.25. All right. If you're given the pKb, then you would need to convert that into a pKa, and then you would be able to find the effective pH range. To convert a pKa into a pKb, don't forget that pKa equals 14 minus the pKb. So it's, again, relatively straightforward in order to convert those. All right, the last thing that we want to talk about in this chapter is buffer capacity. So as I mentioned before, buffers can't resist changes in pH when excessive amounts of acid or bases are added. So what does that mean? Well, it means there is a capacity to the buffer. And it's the amount of acid or base that can be added to the buffer without causing a large change in pH. So let's say we have a buffer that's made with 0.1 moles of HF and 0.125 moles of NaF. Well, first thing we need to ask ourselves is, what is going to react with this HF? That's going to be a strong base, like NaOH. So if I add more than 0.1 moles of NaOH, it will destroy the buffer. It will be above the buffer's capacity. If I add more than 1.25 moles of HCl, which will react with the NaF, that will destroy the buffer capacity. So buffers do have specific capacities. So let's look at the last example from this fairly long section now. It says how many moles of HCl and NaOH separately are required to destroy the following buffers. So if we have 0.125 moles of HF and 0.1 moles of F- in a buffer, how much of these things do we need to add? Well, the first thing is, if we have HF, okay, which one of these two things can possibly destroy the buffer? It's the opposite. This is the acid, so the base, it's what's going to destroy it. So if we add 0.250 moles of NaOH, it will destroy the buffer. F- will react with HCl. So we only need to add 0.100 moles of HCl to destroy this buffer. And technically you'd have to add more than this, right? Slightly more, right? In order to destroy the buffer. But this will destroy the buffer. It says a buffer with 0.1 moles of NH3 and 0.28 moles of NH4+. Well, what is NH3 going to react with? NH3 is a weak base, so it's going to react with the strong acid HCl. So if I add 0.150 moles of HCl, it'll destroy the buffer. This is the conjugate acid of this weak base. So this is going to react with a base, NaOH. So if I add 0.280 moles of NaOH, that will also destroy the buffer. Last question. It says, if you have 100 milliliters of a 0.25 molar formic acid solution, what pH range of buffers can you prepare? What mass of sodium formate should be added to make the buffer with a pH of 4.96? So in order to solve this, we're going to use the Henderson-Hasselbalch equation, which is pH equals pKa plus log concentration of, in this case, the base is NaCHO2 divided by the concentration of HCHO2. So we have the formula. In this case, though, we're given the pH and we're given the pKa as well as the concentration of formic acid. So the variable here is the concentration of sodium formate. But before we do that, I forgot that we didn't answer the first question. What is the pH range of buffers that we can make? Well, this is an easy question because it's plus or minus 1 from the pKa, so we can make 2.74 to 4.74, and 3.96 is right in that range. So in order to do this, the pH that we want is 3.96, which we already know we're going to need more of this, more of the conjugate base than we have of the acid, because the pH is higher than the pKa. So the pKa is 3.74 plus log concentration of NaCHO2 is the variable over 0.250 molar. All right, so in order to do this, we need to subtract that out. So we get, I'm going to move the log over, log of concentration of NaCHO2 over 0.250 equals 3.96 minus 3.74 is equal to 0.22. Now I take the inverse log, so I want to take 10 to this power and 10 to that one, and I get that the concentration of NaCHO2 over 0.250 equals 10 to the 0.22, which is 1.66. Cross multiply, and I find that the concentration of NaCHO2 is equal to 0.415 molar. So it's 1.66 times the other one. A lot of work. Unfortunately, it doesn't ask us for the concentration of it. It asks us for what mass of sodium formate should be added. Well, in order to do that, we need to do dimensional analysis. So we need to convert from liters of solution to moles of sodium formate, and then finally to grams of sodium formate. In this case, we're told we have 100 milliliters of solution. We need to convert that to liters, divide by 1,000. So we have 0.1000 liters of our solution times. Now we need to convert that to moles. In order to convert that to moles, we're going to use the molarity that we just found. And for every 1 liter of the solution, it contains 0.415 moles of sodium formate, NaCHO2. Then we finally want to convert that to grams of NaCHO2, which we put 68.01 grams of NaCHO2 on the top and 1 mole of NaCHO2 on the bottom. So just the molar mass, and I understand this is getting messy here, so I'm going to just do that to divide it. And when I do that, I finally find that I will use 2.82 grams of NaCHO2. So these problems can be very time consuming because there's a lot of steps in order to solve them. So here I had to find the concentration first, and that was a little bit of a problem because of how the math worked. And then I had to use dimensional analysis to convert that concentration into grams. Well, ultimately I converted the liters of solution into grams. So buffer solutions are complicated. This is why in the previous sections we talked about learning the equilibrium stuff was really important, because as we start to apply it here, it becomes more complicated. In the next section, we'll look at titrations. And unfortunately, titrations are probably even a little bit more complicated in terms of what's going on, because sometimes we have a buffer solution. So we're essentially considering buffer solutions within a larger solutions, but we will look at that in the next section.